Was there a before the Big Bang? I've been thinking about this a lot lately. Not just about the beginning of the universe, but what it really means to begin. You know, when we say that time and space were born in the Big Bang, we're not just saying that something happened a very long time ago. We're saying that the very concepts of time and space, those things we use to describe when and where everything is, they didn't exist before that moment. It's quite a radical thing to say, isn't it? The idea is that, well, when you take general relativity seriously, when you take Einstein's great theory of gravity, and you ask it to describe what the universe was like right at the start, at the very, very beginning, it sort of runs into a problem. You get these equations that just, well, they blow up. The curvature of space-time becomes infinite. The density of matter becomes infinite. And we call that a singularity. But what it really means is that the laws of physics, the ones we've been using so successfully for over a century, they just stop working. They stop being predictive. They break down. So then, what you have to ask, what does it mean when your laws of physics break down? Does it mean that the universe truly had a beginning, a sort of first moment? Or does it mean that we're missing something? That maybe there's a deeper layer to reality, something underneath what we currently understand? But if we just stick for a moment with what general relativity tells us, what Einstein's theory says, then time itself is a part of the universe. It's not this thing that exists in the background, this absolute clock ticking away independent of everything else. No, it's woven into the very fabric of the cosmos. It's part of space-time. And so when you say the universe began, you are also saying that time began. It's like asking, what's north of the North Pole? It's not that there's a mountain or a cliff or some hidden land up there. It's just that the concept itself, the direction north, stops making sense. And that's a very, very strange idea because our brains aren't really wired to think like that, are they? We experience time as this constant flow. One thing happens, then another thing happens, and so on. So when you ask someone what came before the Big Bang, it feels like a natural question. It feels like it ought to have an answer. But from the perspective of relativity, from what the equations actually suggest, the question might not even be well formed. There might not have been a before, because before requires time, and time itself, didn't exist. Now that raises all sorts of questions, I mean really deep ones. Because if there was no before, then the universe didn't emerge from anything. It didn't emerge in anything either. It wasn't expanding into empty space. It was space itself that was expanding. And when you look backwards to the very earliest moments, all the way back to that first trillionth of a second, well beyond that our physics sort of fades out. We can describe the expansion beautifully from a fraction of a second onward, but right at the beginning, right at that so-called t=0, we're just not sure what's going on. And that is where quantum theory comes in. Because general relativity, for all its successes, is not a quantum theory. And when you're dealing with something like the beginning of the universe, something that's incredibly small and incredibly energetic, you need quantum physics. You need a theory that merges gravity with quantum mechanics. But we don't have that yet. Not completely. We have candidates, string theory loop quantum gravity and so on, but nothing conclusive, nothing experimentally verified. So we're in this strange position. Our best theory of the large-scale relativity suggests that time had a beginning. But we also know that theory breaks down at that very beginning. We need a quantum theory to describe it, but we don't have a complete one. Stephen Hawking talked about this idea in a very elegant way. He and James Hartley proposed something called the no-boundary proposal, using a concept called imaginary time. Not in the sense of fantasy, but in the mathematical sense, where time behaves more like a spatial dimension. And in that picture, the universe doesn't have a sharp beginning. There's no edge, no boundary, it's more like the surface of the Earth. If you walk south, you eventually reach the South Pole, but there's no edge to fall off. Just a smooth transition in the geometry. In this model, the universe could be finite, but without a start in the way we think of it. Now, whether that's the correct picture, we don't know. But it shows you how flexible our concepts have to become when we're dealing with the origin of everything. It leaves us in this strange, uncertain place. And it's this uncertainty that forces some physicists to ask a different question. What if what we call the Big Bang wasn't the beginning at all? What if it was just a transition point, a moment not of creation but of transformation, part of something much, much older? This is a different picture. There's a picture I think that's beginning to form in modern cosmology, which is quite different from the traditional one, the one we all learned in school. That idea of the universe beginning from a single infinitely dense point, an explosion, a singularity, and expanding outwards ever since. It's an elegant idea, and it's simple, and for a long time it made sense. But now there's a different possibility being taken very seriously, a different rhythm if you like, one that suggests the universe doesn't have a single beginning and a single end, but instead it oscillates, it breathes. This is the idea of the cyclic universe. It's not just a single event, one explosion followed by a slow cold fading. It's a repeating process, an expansion like the one we're in now, followed by a long slow contraction, a collapse, and then a new expansion, over and over, maybe infinitely. And what's fascinating is that this isn't just mythology or poetry, though it sounds like it. It's based on physics, on equations, on models, on things that could potentially be observed. It's not proven, of course. It's speculative, but it's grounded speculation. And the thing that really makes this picture possible is the idea that the Big Bang wasn't a beginning at all, but a bounce, a big bounce. So instead of everything starting from nothing, from that singularity where our physics breaks down, it might have emerged from a previous universe. A cosmos that had lived its own life, expanded and then collapsed back in on itself and then rebounded. It's a radical change in thinking. We're not talking about creation ex nihilo anymore, creation from nothing. We're talking about a universe that cycles through phases, each one following from the collapse of the last. The first time I read about this, I remember thinking, hang on, but what about entropy? I mean, that's the big problem, isn't it? The second law of thermodynamics, the arrow of time. Disorder always increases. A glass falls and shatters. It doesn't spontaneously reassemble itself. A star burns out, radiating its heat into the void. That heat doesn't just gather itself back together. Entropy, this measure of disorder, it always goes up. So if you go through a cycle, if you've got stars forming and burning out and black holes merging and growing, you're building up disorder. You're building up entropy. The universe is getting messier and more diluted with waste heat. So how could you possibly keep resetting? Wouldn't each new cycle start with all the built-up entropy from the last one? Wouldn't each cycle be more chaotic, more diluted, more dead than the last? Eventually, wouldn't the universe just die of heat death after a few cycles, unable to form new stars, unable to do anything interesting? It seems like an unbreakable law, but that is exactly where it gets interesting. Because the newer models of the cyclic universe, the ones developed by physicists like Paul Steinhardt and Neil Turok, they suggest mechanisms that might, solve this. They propose that the problem isn't with the law of entropy, but with our assumptions about the bounce. In these models, the bounce itself, this moment of extreme compression, acts as a massive entropy reset, or more accurately, a dilution. As the universe collapses, all the matter and radiation are squeezed together. But in some of these models, the energy that will drive the next expansion isn't this old matter. It's stored in the fabric of space itself, in a scalar field, much like the one that drove inflation in the other model. When the bounce happens, this field's energy is dumped into the new universe, creating new hot matter and radiation. A fresh start. The old high-entropy junk from the previous cycle is so incredibly diluted by the physics of the bounce, it's as if it was never there. The new universe is born, clean, smooth, ordered, low entropy. It's deeply counterintuitive, but then again, most things in cosmology are. In these models, space and time, they never really vanish. There's no singularity, no point of infinite density where the rules disappear. There's always a before, there's always an after. The universe just goes through these epochs, these eras of expansion and contraction linked by bounces. They're not catastrophic ends, but transitions. And there's this idea in some versions that time might be infinite in both directions, not just extending forever into the future as our universe expands, but stretching endlessly into the past as well. So our Big Bang, our 13.8 billion year history, is just the latest beat in an eternal rhythm. And what's so elegant about this, I think, is that it solves some of the same awkward features of the standard model, the same ones that the theory of inflation was designed to fix. For instance, that horizon problem. Why is the universe so smooth? Why is it so uniform in all directions? When we look at the cosmic microwave background, that first light from the universe, it's almost exactly the same temperature everywhere. In the standard Big Bang model, regions on opposite sides of the sky were never in causal contact. They never had time to talk to each other, to exchange heat and even out their temperature. So why are they the same? The theory of inflation solves this by saying that in the very first fraction of a second, the universe expanded exponentially fast, blowing up a tiny connected patch into this vast, smooth cosmos. It's a violent, rapid solution. But the cyclic models, they offer a different, almost more patient solution. If the universe had a previous phase, a long, slow period of contraction, then there was plenty of time. trillions of years perhaps. Plenty of time for everything to homogenize, for equilibrium to be reached, for the temperature to smooth out before the bounce ever began. The universe is smooth not because it was stretched in a hurry, but because it had eons to settle down. But the bounce itself, that's the key, that's the mystery, isn't it? What actually happens at that moment of collapse when the universe stops expanding and starts contracting, and then reverses direction again? That's where our current theories get fuzzy. That's where we need quantum gravity. General relativity on its own just gives you a crunch, another singularity. It predicts that the universe will collapse into an infinitely dense point just like the one it supposedly started from. The theory breaks. But when you add quantum mechanics to the picture, things change. In models like loop quantum gravity, for example, there is a smallest possible size. Space itself is quantized. It's made of discrete loops or atoms of space-time. You can't squeeze it down to zero. So as the universe collapses, it gets smaller and smaller, denser and denser, until it hits this fundamental limit, this quantum foam. And at that point, the quantum nature of gravity itself becomes repulsive. It pushes back. It's like compressing a spring. You squeeze it, you push it inward, and all that potential energy builds up. And at some point, the spring's own structure refuses to be compressed any further. It pushes back violently. The energy stored in the compression becomes the driver of the next expansion. That's the big bounce, not a singularity, but a moment of minimum size and maximum density, a turning point governed by a new set of laws we are only just beginning to guess at. But that just raises more questions, doesn't it? Do structures survive, or does anything survive at all? Is there a memory of previous cycles? Could anything carry through from one phase of the universe to the next? Some physicists think maybe yes. Not a star or a galaxy, those would be torn apart, but maybe certain fundamental properties. Maybe the overall curvature of the universe or its topology. Maybe it bears the scars of earlier cycles. There's this tantalizing thought that buried deep in the noise of the cosmic microwave background, in the patterns of how galaxies are clustered, there might be signatures, anomalies, faint patterns that are echoes of events that occurred not just billions but trillions of years ago. In a previous version of the cosmos, the thought was that we might be able to see echoes not just from our own cosmic infancy, but from a time before this time. And this all changes the way you feel about the universe, about time especially. Because if the universe really is cyclic, then time is not linear. It's not a straight arrow from a single past to a single future. It's more like a circle, a great cosmic loop. And that raises questions about determinism, about fate even. If everything repeats, will it repeat exactly? Or does each cycle with its quantum bounce introduce tiny new variations, tiny random uncertainties that get magnified over the next eon? Could those variations build up over time? Could they allow something new to emerge? There's something oddly comforting in the idea of a cyclic cosmos. It takes the loneliness out of the void. Instead of a one-time event, a cosmic accident, a universe that came from nothing and will one day fade into a cold, dark, empty nothing, we have a pattern. We have continuity. A sense that the universe is eternal, not static but dynamic, always moving, always changing, always returning. But there's also a kind of melancholy to it, isn't there? Because if everything repeats, if all of this has happened before and will happen again, then what does that say about us as about our lives? Are we just echoes? Is every thought we have, every action we take, every love we feel, just one iteration in an infinite sequence? A story reread over and over? Or is there room for novelty, for creativity, for genuine, unrepeatable change? It's a profound philosophical challenge as well as a scientific one. And I think that's what makes it so compelling. These models aren't just technical tools. They touch on something deep, something almost ancient. The idea of cycles of great ages. It's been around for millennia. In myth, in religion, in philosophy. The Kalpas in Hinduism, the great year of the Stoics. This idea that the world is born, lives, dies, and is born again. Now, physics is finding ways to bring those old intuitions into a modern mathematical framework. And if in the end, if we discover that the universe does cycle, that it expands, collapses, and expands again, then we'll have to rethink everything we thought we knew about beginnings and about endings, about time and cause and existence itself. Because it would mean that there was no ultimate origin, no final destination, just an eternal dance. A rhythm written into the structure of reality, a rhythm that we have only just begun to hear. But there is another way to think about it. It's an idea that steps away from that eternal ancient rhythm of the cyclic universe and instead asks a question that is in some ways even more profound. What if the universe didn't come from a previous state? What if it didn't come from a bounce or a collision? What if it came from nothing? Now that word, nothing, is probably the most loaded word in our language. When we in our everyday lives think of nothing, we think of absence, a complete void, no space, no time, no matter, no energy, no rules, a perfect, absolute, silent blackness. But in physics, in quantum physics, that's not really how it works. There's this strange and wonderful idea that the vacuum isn't really empty. It sounds like a contradiction in terms, doesn't it? Vacuum by definition is emptiness. If you take a box and you pump out all the air and you shielded it from all radiation and you cool it down to absolute zero so there's no heat, you would think you'd be left with nothing. But quantum field theory says no. It says that even in the quietest, most empty, most perfectly isolated patch of space imaginable, there is still something happening. Tiny fluctuations, a kind of restlessness, a sort of bubbling quantum sea. The uncertainty principle, which we usually think of as applying to knowing things like a particle's position and momentum, has a deeper form. It also applies to energy and time. It means that for very, very short moments, energy can be borrowed from the vacuum as long as it's paid back almost instantly. And in that borrowed moment, particles can flash into existence. A particle and its antiparticle, an electron and a positron, for example. They appear from the nothingness, they exist for a fraction of a second, and then they find each other and annihilate, disappearing back into the potential from which they came. The vacuum is seething with this act of VA, a wild, unpredictable foam of possibilities existing just beneath the surface of the reality we can measure. This isn't just a theoretical quirk, it's not just a mathematical fantasy. This vacuum energy, it is real. It has been measured. There's a phenomenon called the Casimir effect. It's a very elegant and subtle experiment. If you take two perfectly smooth, uncharged metal plates, and you bring them incredibly close together in a perfect vacuum, closer than the width of a human hair, a force will appear between them, a measurable physical force pushing them together. What is this force? It's the vacuum. It's the pressure of all those virtual particles, all that quantum foam fluctuating in the space outside their plates being greater than the pressure of the fluctuations that can fit between them. It is the void, making its presence known. It is real physical energy emerging from what we thought was emptiness. So, if you start from that, if you start from the idea that empty space isn't really empty, that the vacuum is a place of restless, bubbling energy, that opens up something extraordinary. Because if even nothing isn't really nothing, then maybe you don't need a whole universe to start with. Maybe a universe, or rather the seed of one, can emerge from one of these fluctuations. In the early 70s, a physicist named Edward Tryon said something that at the time sounded almost like a joke. He was giving a lecture and he said, "I offer the modest proposal that our universe is simply one of those things which happen from time to time." What he meant was, maybe the universe is just a quantum fluctuation. A particularly large and particularly long-lived one, but a fluctuation nonetheless. At first, that sounds impossible. How can you get this, all the billions of galaxies, the trillions of stars, the sheer stuff of reality, from a tiny random burp in the vacuum? Wouldn't that violate one of the most fundamental laws we know, the conservation of energy? You can't create energy from nothing, you can't just make a universe. But this is where the idea gets truly breathtakingly elegant. The total energy of the universe might be zero. It's a kind of cosmic accounting. Think of it this way. Imagine you're standing on a perfectly flat, level piece of ground. You dig a hole, you've created a hole, a negative space, but you've also right next to it created a pile of dirt, a positive mound. The dirt from the pile is exactly equal to the missing dirt from the hole. The net amount of dirt on the land hasn't changed. The total is still zero. The universe could be like that. All the matter and energy we see, the stars, the radiation, the dust, the light, everything, that's the positive energy. That's the pile of dirt. But gravity is an attractive force. To pull matter apart, to move it up against the pull of gravity, you have to add energy. This means that gravity itself, the gravitational field, acts like a negative energy. It's the whole. And the calculations show that it's entirely possible, even plausible, that the total positive energy of all the matter in the cosmos is perfectly balanced by the total negative gravitational energy of that same matter. So the total energy of the universe is zero. It all balances out. And if the total energy is zero, then you don't need to create energy to make a universe. You don't violate any conservation laws. You just need to separate the positive from the negative. It could in principle arise from a fluctuation in the vacuum without any cost. You could in a sense get a universe for free, but it feels like a cheat, doesn't it? There's a philosophical catch that's hard to ignore. We're saying that something came from nothing, and yet the nothing we're talking about, this quantum vacuum, it's full of potential. It's a structured void seething with virtual particles, and it is governed by the laws of quantum mechanics. The uncertainty principle, quantum field theory, those are the rules that allow the fluctuation to happen in the first place. So then the question just gets pushed back a step, doesn't it? Where did that come from? Where did the quantum vacuum get its properties? Where did the laws of physics come from? Are those laws eternal? Were they always there, existing in some abstract platonic realm, just waiting for a universe to apply to? What are laws anyway, if there's no universe yet for them to act on? Where are they written? It's one of those questions that sounds simple, but when you dig into it, you find yourself standing on shifting ground. It's hard to tell whether you're talking about physics or metaphysics anymore. Some physicists have argued that this is good enough, that a quantum vacuum is as close to nothing as you can physically get, that this nothing is inherently unstable and it inevitably produces something. But others are less convinced. They feel that until you've explained the origin of the vacuum itself, the origin of the laws governing the vacuum, you haven't really explained the origin of the universe. You've just moved the problem around. And I think that's okay. I think it's part of the process. Because what physics is doing here isn't offering a final absolute answer. It's constructing a chain of reasoning, each link based on what we can calculate, what we can model, what we can measure. And the quantum vacuum is part of that chain. It's not an ultimate beginning maybe, but it's a step, a profound step toward understanding how complexity, structure, and ultimately life could emerge from simplicity, from apparent emptiness. But there's one more piece to the puzzle. A quantum fluctuation, even a big one, would be tiny, microscopic, unimaginably small. So how do you get from a microscopic speck to the vast, observable universe we see today, 13.8 billion years later, stretching 93 billion light-years across? That is where another crucial idea comes in. Inflation. This is the theory that in the very first fraction of a second of its existence, a sliver of time so small, it's hard to even write down, the universe underwent a period of violent exponential expansion. Driven by the energy of a false vacuum, a high-energy state of that quantum field space itself stretched. It didn't just expand, it inflated, doubling in size and doubling again and again and again, dozens and dozens of times, all before the first picosecond was over. A tiny quantum-sized patch smaller than a proton would have been stretched to something the size of a marble in the blink of an eye, and then it just kept going. This burst of inflation would have taken that initial microscopic quantum fluctuation and magnified it to astrophysical scales. It would smooth out all the wrinkles, flatten the geometry of space. And then, as this inflationary period ended, that energy decayed, releasing a flood of matter and radiation. That would be the hot Big Bang we observe. The Big Bang in this picture isn't the origin, it's the afterglow. It's the moment the inflationary engine shut off and the universe became hot and dense and settled into the more leisurely expansion we've been in ever since. So you have this two-part process. First, a quantum fluctuation, a bubble from the void, a universe seed with zero net energy. And second, an inflationary trigger of that takes that seed and expands it into a cosmos. But this combination leads to one final staggering thought. If the quantum vacuum is this eternal restless sea, and if these fluctuations can happen, and if inflation is a process that can be triggered by those fluctuations, why would it only happen once? If the conditions for this are just part of the fabric of the vacuum, then couldn't it be happening all the time and in all different places in that quantum foam? Couldn't there be other fluctuations in other regions that also underwent inflation, blossoming into their own separate universes? Bubbles forming and expanding completely isolated from ours, separated by a vast inflating ocean of quantum vacuum. You don't just get one universe, you get a multiverse. A vast, perhaps infinite collection of universes all emerging from the quantum restlessness of the void. Ours is just one of them, one bubble among a potentially endless number. This idea, it takes everything we thought we knew about the universe, about its scale, its beginning, its uniqueness, and it stretches it beyond anything we can quite visualize. It's called eternal inflation. And it's one of those concepts that once you hear it, you can't quite let it go, because it doesn't just explain why our universe looks the way it does. It suggests that ours is only one of countless others. Like a single bubble in an endless cosmic sea, It starts with the basic inflation idea we just touched on, that in the first moment the universe underwent this burst of exponential expansion. That theory is fairly standard now. It explains so much about why our universe is so flat and so homogeneous, why distant regions of the sky look so similar even though in the standard model they shouldn't have had time to interact. But what some models of inflation suggest, what the mathematics seems to imply, is that inflation might not have ended everywhere at the same time. Instead, picture the quantum field that drives this inflation, not as a smooth surface, but as a vast churning ocean. It's a quantum field, which means it fluctuates. It's inherently random. In some regions, by a random quantum fluctuation, the field cools down. It decays. It rolls to the bottom of its energy valley. The inflationary energy is released and a bubble of normal space and time forms. A hot Big Bang happens. A universe like ours is born. But in the regions around that bubble, the field doesn't decay. By another random fluctuation, it stays high up in its energy state, and in those regions, it keeps inflating. The space between those bubbles, it just keeps growing exponentially, eternally. It's like a pot of water gently boiling. The inflationary space is the water, and every so often a bubble of steam nucleates and expands. That's a universe. But the water itself doesn't all turn to steam at once. It just keeps bubbling, creating more steam, more bubbles in a process that never ever ceases. And because the water, the space between the bubbles, is inflating so impossibly fast, the new bubbles are driven apart from each other at speeds far, far greater than the speed of light. They almost instantly become causally disconnected. Each bubble is its own self-contained cosmos, forever isolated, unaware of the others. The whole structure, the multiverse, is this never-ending self-reproducing process of expansion and nucleation. Our universe, this vast ancient place we think of as everything, might be just one tiny part of this much, much larger structure. A pocket, a fluctuation, one possible outcome in an infinite landscape of outcomes. And that has implications that are almost too large to hold in your mind. Because if this is true, then the laws of physics as we know them, they might not be fundamental. They might just be, They might be specific to our bubble. Think of it this way. In some theories like string theory, there isn't just one way for physics to be. There isn't just one set of rules, there's a landscape of possibilities. A vast multi-dimensional terrain with perhaps 10 to the 500 different valleys. Each valley represents a different stable vacuum state, a different self-consistent set of laws. When a new bubble universe forms, it's like a ball rolling down this vast landscape. Where it settles is random. And the valley it settles in, that determines its physics. So in one bubble, the speed of light might be different. The strength of gravity might be stronger or weaker. The mass of the electron, the charge of a quark, all these numbers that we've so carefully measured, the numbers that define our reality, they might be different. In some bubbles, there might be 4 dimensions of space, in others 9. In some, the forces we know might not exist at all, replaced by others we can't imagine. Most of these universes in this picture would be sterile, dead. If gravity were just a little bit stronger, the universe might have collapsed back on itself a second after it formed. A little weaker, and stars and galaxies would never have coalesced. If the nuclear force that holds atoms together were slightly different carbon atom, the basis of our biology might not be stable. Life as we know it would be impossible. Our universe seems fine-tuned. It's balanced on a knife edge of parameters, all of which seem to be just right for complexity, for structure, for life to emerge. For a long time this was a deep mystery. Why? Why this precise Goldilocks set of rules? It looked to some like evidence of design, of a purpose. And the multiverse of eternal inflation, it offers an answer. It's not a mystical answer, it's just statistical. It says that in an infinite or near infinite multiverse, every possible combination of laws will be tried out in some bubble somewhere. The vast majority of those bubbles will be empty, dark and lifeless. But a tiny fraction, purely by chance, will happen to have the right combination of laws for stars to form, for planets to congeal, for chemistry to happen, and, eventually, for consciousness to arise. And we, being conscious observers, must find ourselves in one of those rare life-permitting bubbles. It's not that the universe was designed for us, it's that we could only have evolved in a universe that allowed for us. This is the anthropic principle. And for a long time it felt unsatisfying. It felt like a philosophical cop-out. Things are the way they are because we are here to see them. But in the context of eternal inflation, it's not philosophy. It's not a cop-out. It's a consequence of the theory. It's a selection effect. You can only win the cosmic lottery if there are an infinite number of tickets being drawn. But here's where it gets even stranger. Because if inflation is eternal into the future, if this sea is always bubbling, always creating new worlds, what about the past? Does this eternal process have a beginning? Some of the most prominent physicists in this field, like Alan Guth and Alex Vilenkin, have argued that this process, it might also be eternal into the past. They proved a theorem suggesting that while any single bubble universe like ours must have a beginning, the inflationary sea itself, the multiverse, may not. That there might not have been a first bubble, that the process of inflation and bubble creation might extend infinitely backwards in time, or in whatever passes for time in that inflationary background, because time itself might be local different inside each bubble. If that's the case, then the multiverse has no beginning, it has no origin, it just always existed, always inflating, always spawning new regions, new possibilities, which means there was never a single absolute Big Bang. Our Big Bang, the event we trace back 13.8 billion years, was just the local reheating. It was the moment our bubble decayed from the inflating vacuum. It was the beginning of our chapter, but it wasn't the beginning of the book. The book may be infinite. And what does that feel like? To think that this entire cosmos, everything we can see, everything we've ever measured, everything we've ever called the universe, is just one of, perhaps, infinitely many. In some of those bubbles there are no stars. In others the laws are so alien we couldn't even describe them. And in others, in an infinite set, there might be variations of us. Worlds where everything is almost the same, but just, you made a different choice this morning. Worlds where the dinosaurs never went extinct. Worlds where, well, in an infinite set, every possibility that is not forbidden by the fundamental laws is realized. It can feel diminishing. It can make you feel impossibly small, not just a speck in one galaxy among billions, but a speck in one universe, among an infinite self-reproducing fractal of universes, a random flicker in a vast indifferent machine. But it can also feel liberating. It means that existence doesn't need a single reason. It doesn't need a single ultimate design. It just is. It is what happens when quantum fields are left to their own devices in the fullness of eternity. It's a process that generates complexity from simplicity, structure from randomness, and consciousness from physics. It reframes us. We are not the center of the universe. We are not even the center of a universe. We are perhaps just a thought, a pattern, a single complex ripple in an ocean of eternal creation. A universe or a multiverse where the Big Bang isn't the beginning. It's just the start of our story. A story that began in a bubble, one bubble among countless others, all drifting, all expanding, all born from a restless eternal sea. But all of these ideas, the eternal cycles, the sea of bubbling universes, they mostly assume that the world we inhabit is, well, all there is, that our 3 dimensions of space and one of time are the entire stage. There is another path, a different way of thinking. It comes from the deepest, most ambitious quest in all of physics, the attempt to find a single unified theory, a theory of everything, an equation maybe just an inch long that could describe, well, everything. All the fundamental forces, gravity which holds the planets, electromagnetism which is the light that fills this room, and the strong and weak nuclear forces which hold our very atoms together. All of them emerging from one single elegant mathematical structure. And the leading candidate for this, for decades, has been string theory. The idea is so simple to state, but its consequences are vast. It proposes that if you could zoom in, if you had a microscope powerful enough to look past the molecules, past the atoms, past the electrons and quarks, if you could look at the truly, truly fundamental building blocks of reality, you wouldn't find points. You wouldn't find tiny zero-dimensional dots. You would find strings, tiny one-dimensional vibrating filaments of energy. And in this picture, every particle we see, the electron, the photon, the graviton, all of them, they aren't different things, they're just different notes, different vibrations of the same fundamental string. An electron is a string vibrating in one way, a photon is a string vibrating in another, a quark another. It's a cosmic symphony. All the complexity we see, all the different particles and forces, all of chemistry, all of life is just music. The harmonics of these one underlying vibrating strings. It's an idea of profound, profound elegance. But there's a catch. Of course there is. When you write the equations for this theory, when you try to make the mathematics work to make it consistent and predictive, it It just doesn't work. The math breaks down. It gives you infinities and paradoxes and nonsensical answers. It doesn't work in three spatial dimension. The equations only fit together. They only become consistent. They only sing if you add more spatial dimensions, more directions to move through. Usually the theory requires 9 or 10 spatial dimensions for a total of 10 or 11 space-time dimensions, which leads to a very natural, very obvious question. Where are they? If there are, say, 6 other directions of space all around us right here, right now, why can't I see them? Why can't I just reach out my hand and move it into the 5th or 6th or 7th dimension? For a long time, the answer was an idea called compactification. It's the idea that these extra dimensions exist, but they are rolled up, curled up so tightly, so ridiculously small that we simply don't notice them. Think of a long, thin garden hose stretched across a yard. From a great distance and from a bird's eye view, it looks like a one-dimensional line. It has only length. But if you are a tiny ant walking on the hose, you know better. You can walk along the hose, yes. That's the big obvious dimension. But you can also walk around it. There is a second dimension, the circumference of the hose, that is simply too small to be seen from far away. String theory suggested that these extra dimensions are like that. At every single point in our 3D space, there is a tiny curled up shape, a 6-dimensional geometry, so small on the Planck length, the smallest possible scale in physics, that we would never ever perceive them in our everyday low energy world. And that was the thinking for a long time. It's an elegant way to hide them. But then a different possibility emerged. A twist that came from an evolution of string theory called M-theory. What if the extra dimensions aren't all small? What if some of them are large? And what if we are the ones who are confined? This is the brain idea. Brain is short for membrane. The idea is that our entire universe, everything we can see, every galaxy, every star, every particle that makes up our bodies, every force except gravity, is confined to a 3-dimensional brain. Picture our universe as the 2-dimensional surface of a pond. We are like creatures, water striders, who can only move on that surface. We can move left, right, forward, back, but we have no concept of up or down into the depth of the water. In this model, our 3D universe is just such a surface, a 3-brain, floating inside a much larger, higher dimensional space, a space called the bulk. The particles that make us up the strings, they're open strings with their ends anchored to this brain. They can't leave, they're stuck here. Light can't leave, electrons can't leave. We are stuck to this 3-dimensional membrane. But gravity is different. In this theory, gravity is not an open string, it's a closed string. A little loop. And because it has no ends to anchor it, it's not confined to our brain. It can leak. It can travel off our brain and into the bulk, into those extra hidden dimensions. And this offers one of the most stunning and elegant explanations for one of the deepest mysteries in physics. Why is gravity so weak? It sounds like a strange question. Gravity holds us to the Earth. It holds the Earth in orbit around the Sun. It holds these galaxies together, though it seems powerful. But compared to the other forces, it is impossibly weak. Think about it. A tiny, tiny refrigerator magnet can pick up a paperclip, defeating the entire gravitational pull of the entire planet Earth. The electromagnetic force of that little magnet is vastly, absurdly stronger than the gravity of a 6 trillion kilogram planet. Why? Why this huge discrepancy? The brain world idea gives an answer. Gravity isn't really weak. Well, it's just as strong as the other forces, but we only feel a tiny fraction of it, because most of its strength has leaked away. It has been diluted, spreading out across those extra unseen higher dimensions of the bulk. We are only feeling the whisper of gravity that manages to stick to our brain. What an astonishing thought. Now, if you take that idea seriously, that we live on a membrane in a higher dimensional space, it opens up a completely new and truly radical possibility for the Big Bang. Because if our universe is a brain, what if there are others? What if floating in that higher dimensional bulk there are other brains, parallel universes, not in the quantum sense but literally in a parallel, stacked perhaps, separated from us by a tiny distance, in a direction we cannot point to, a direction we cannot perceive? And what if these brains are not static? What if they are moving? What if they can collide? This is the basis of the ekprotic model, a name that means born from fire. It proposes that what we call the Big Bang was not a singularity. It was not a beginning from nothing. It was an impact. It was the cataclysmic universe-shattering collision of our brain with another. Imagine these two vast three-dimensional surfaces drifting through the higher dimensional bulk, perhaps drawn together by a force like gravity, moving closer and closer over trillions and trillions of years in a cold, dark, quiet state, until, clap, the energy released in that collision would be unimaginable. The kinetic energy of these two massive membranes smashing into each other would be converted in an instant into a perfect hot fireball, a plasma. That would fill our brain, our universe, with the matter and radiation that would become the stars and the galaxies and us. And that fireball, that bang, would be the starting point for our cosmic history. The cooling, the expanding, the forming of atoms and stars and galaxies. In this picture, the Big Bang isn't the origin of space and time, it's just an event, a local event that happened on our brain. And before the Big Bang, before the collision, there was a before. It was the time when these two brains were approaching each other. A cold, dark, empty state. It completely avoids the singularity. It completely avoids the problem of a T-zero where physics breaks down. And this too can be a cyclic model. The brains collide, they expand away from each other. That's our universe expanding. The expansion driven by the collision's energy smooths them out, cools them down. Eventually, perhaps, they are pulled back together by some force, they contract, and they collide again. A new Big Bang, a new universe, a new cycle. And this model, it solves those same cosmological puzzles like the horizon problem. Why is the universe so smooth? Not because of a rapid, violent inflation, but because the brains had a vast, perhaps infinite amount of time to smooth themselves out before they collided. They were like two giant, perfectly flat cold sheets, floating in the bulk, and they had eons to settle down. The smoothness was their initial state. It's a much more patient solution. What a thought, that our entire reality is just a slice, a membrane, that we are living in a shadow of a much larger, much richer, higher dimensional reality, that our universe is not a closed system. The story of our origin is not contained within our cosmos. It is entangled with something outside, something in the bulk. It makes you wonder, are there other brains out there? Other universes with different physics, different constants, different dimensions floating nearby? Could we ever know? Well, maybe. Remember how gravity can leak, maybe. Gravitational waves, those ripples in space-time that we've only just begun to detect. Maybe they aren't entirely confined to our brain. Maybe, if we listen closely enough, we could one day detect a signature, a gravitational echo of the bulk, or of another brain, a whisper from that hidden higher dimensional space. It's speculative. We don't have direct evidence for these hidden dimensions. We might never, but the mathematics, it's so compelling. It's not just complexity for the sake of it. It's about unity. It's about finding a framework where all the pieces fit. And when you try to build that framework, the math seems to demand more dimensions. Not as decoration, but as necessity. Hidden, yes, but foundational. And if those dimensions are real, and if they were involved in our beginning, then we get a glimpse. Not a clear view, but a glimpse of what before might really mean. Not a before in our time, but a before in the geometry, in the configuration of that higher dimensional space that cradled our universe before it ignited. We've been on such a journey. We've explored these vast, incredible ideas, universes that breathe in and out, bouncing through eternity. We've imagined an endless, bubbling sea of quantum foam spawning infinite bubble universes. We've even pictured our reality as a thin brain, a membrane that was set ablaze by a collision with another in a higher hidden dimension. And all of these models, they're beautiful, and they're all attempts to answer that one simple question, what came before the Big Bang? But what if the problem isn't in our answers, but in the question itself? What if the deepest mistake we're making is in that one simple word we've just accepted without challenge? Before, that word assumes, it requires, that time is a given, that time is this absolute universal river flowing constantly from a past through the present into a future. But that's not what time is, not according to our best theories of physics. It's quite odd, really. When you ask about what came before, you're assuming that time is this constant background thing, this ticking clock that just keeps going independent of everything. But that's not how time works in general relativity. That's not what Einstein showed us. In that framework, time and space aren't separate things at all. They're not a stage and actors, they are a single unified entity, this four-dimensional fabric we call space-time. And the important bit is, space-time is dynamic. It bends, it stretches, it curves in the presence of matter and energy. Time is part of the geometry. It's not a river that flows, it's a direction. It's a dimension, just like up or left. And this is the bit that's hard to wrap your head around. This leads to an idea, it's been around for a century, called the block universe. The idea is that if time is just another dimension like space, then maybe the past, the present, and the future all exist equally. Right now, that the universe isn't a story that's happening, it's a story that is already written. It's like a loaf of bread. You can slice it at different points, and each slice is a now, a present moment. But the whole loaf, the past, the present, the future, it's all just there. The dinosaurs aren't gone, they are just in a different slice of the block. Your future is also just in a different slice. And what we experience as the flow of time, this powerful, undeniable feeling of moving from one moment to the next, maybe it's an illusion, a trick of our consciousness. Our minds are reading the block slice by slice and creating the sensation of passage. Or perhaps it's not just our minds, perhaps it's physics. There's only one law in physics that seems to care about the direction of time, the second law of thermodynamics, the law that says entropy, disorder, always increases. A glass shatters, it doesn't unshatter. An egg cooks, it doesn't uncook. This gives time an arrow. So maybe the flow of time is just our minds and our bodies registering this irreversible increase of entropy. We are moving from a more ordered slice of the block to a more disordered one, and that's all flow is. Now, if you accept that time is just a geometric dimension in a static block universe, then the question what came before the Big Bang, it changes. The Big Bang isn't a moment anymore, it's a place. It's the edge of the block, it's the first slice of the loaf, it's the boundary of space-time. And so we're back to that problem. What created the edge? What is beyond the edge? And this is where Stephen Hawking's idea, the one we touched on, comes back, but in a much deeper, more profound way. This idea of imaginary time. It's one of those concepts that sounds like fantasy, but it's not, it's mathematically precise. Hawking and his colleague James Hartle were trying to build a quantum description of the universe. They were trying to apply the strange rules of quantum mechanics to the entire block of space-time, and they ran headfirst into that edge, that singularity, that T0, a place where the geometry breaks, where the equations give you infinity. So they tried something, a trick. It's a mathematical technique that physicists sometimes use to solve very hard problems. It's called a Wick rotation. You take the variable for time, t, and in your equations you replace it. You replace it with I times t. I being the imaginary number, the square root of -1. Now you don't need to understand the math, I barely do, but you need to understand what this does. When you do this in the equations of cosmology, a kind of miracle happens. The singularity, that nasty broken edge of the block, it vanishes. It just smooths out. What does that mean? It means that as you go back and back and back towards the Big Bang, time stops behaving like time. It rotates, and it starts behaving just like another dimension of space. It's that North Pole analogy again. If you are walking on the surface of the Earth, you can go north. That's a direction. But when you reach the North Pole, the direction north vanishes. You can't go north of the North Pole, and there is no edge to fall off. There is no beginning of the Earth's surface at the North Pole. The geometry just smoothly, perfectly curves. This is what Hawking's no-boundary proposal is. It's the idea that the universe, when you look at it in this imaginary time, is finite. It has a finite size, but it has no beginning. No edge, no boundary, no singularity. It just is. It's self-contained. It doesn't need a before. It doesn't need a creator. It doesn't need an external cause, because it never had a start in that sense. The universe, in this view, simply is. And what we think of as the Big Bang, what we experience as real time, that's just a property. It's what emerges from this timeless, boundaryless geometry as it expands. Real time is the emergent property, not the fundamental one. At the deepest layer, the universe may be timeless. This leads to an even stranger, more fundamental idea. When you try to apply quantum mechanics to the whole universe, you have a conceptual problem. The normal equation of quantum mechanics, the Schrödinger equation, is beautiful. It describes how a quantum system, an atom, an electron, evolves in time. It has t, the variable for time, written all through it. But if your system is the entire universe, if your system is everything, including space and matter and time itself, what does it evolve in? Where is the external clock to measure its t? There isn't one. Decades ago, two physicists, John Wheeler and Bryce DeWitt, tried to write this equation, the Schrödinger equation for the universe. And when they did, when they wrote down the master equation for the entire wave function of the cosmos, they found something baffling. The variable for time, it's not there. It just cancels out. It disappears from the final equation. The master equation that describes the entire cosmos, all of reality, is static. It is timeless. It doesn't describe a quantum that happens. It describes a universe that is, this is known in physics as the problem of time, and it's one of the deepest, most profound mysteries we have ever uncovered. It suggests that at the most fundamental level, nothing is happening, nothing is changing. The block universe is real. The equation describes all the slices of the loaf all at once. It describes a static, timeless shape. So, if that's true, then time and change and history and the flow we feel, they must be emergent. They are not fundamental. They are a property of how we as observers inside the system perceive this static, timeless block. It's a relationship between parts of the block, not a flow of the block. How do you even think about that? That at the most fundamental level there is no before and no after. There is just is. That everything you've ever done and everything you ever will do isn't happening. It's just there, a pattern, encoded in this timeless universal wave function. It's humbling. It's the ultimate challenge to our intuition. So when we ask, what came before the Big Bang? We are asking a question that is steeped in our deepest, most human, most fundamental intuition that time is a river that flows. But maybe the universe at its core is not a story. Maybe it's still not a sequence. Maybe it's a shape. A static, silent 4-dimensional or 11-dimensional geometry. And we are just a pattern, a complex conscious pattern, tracing a path through it. Maybe the question isn't what came before. Maybe the question is, what is at the edge? Or maybe there is no edge at all. It's a strange place to be, isn't it? We've travelled so far. We've stood on the edge of an eternal bouncing universe. We've swum in a quantum foam that gives birth to infinite bubbles. We've pictured our reality as a thin membrane set ablaze by a collision in a higher dimension. We've even dared to ask if time itself is just a feature of our perception, a geometric property of a static, timeless block of existence. All of these ideas, they stretch physics and they stretch our minds to the absolute breaking point, but they all share one final assumption. They all assume that physics is real, that the laws we're discovering, quantum mechanics, relativity, string theory, are the base code of reality. What if they're not? What if we take one final radical step? What if all of this entire vast, intricate structure, the physics, the time, the hidden dimensions, the 13.8 billion years, what if it's not the base reality? What if it's a simulation? I mean, it sounds like science fiction. It sounds like a movie. It's a plot device. But it's also a serious philosophical and even scientific question. It's not just a wild guess. It's a logical argument. There's a philosopher at Oxford, Nick Bostrom, who proposed this thing called the simulation argument. And it's not a proof that we are in a simulation. It's a trilemma. It's an argument that one of three very unsettling things must be true. The first possibility is that all advanced civilizations everywhere go extinct. They hit some great filter, nuclear war, climate change, a rogue AI, and they never reach a stage of technological maturity where they could create, well, a universe. The second possibility is that civilizations do reach that stage and they get post-human. They have the computational power to simulate entire conscious worlds, but they choose not to for some reason. Maybe it's an ethical taboo. Maybe it's just boring to this. The third possibility is that they do run these simulations. And if that third one is all true, if any civilization anywhere ever reaches this point and starts running ancestor simulations, or just artificial universes for research or for art, or just because they can, then what happens? They wouldn't just run one, they'd run thousands, millions, billions, and over time the number of simulated realities the number of simulated conscious minds like ours, would come to vastly astronomically outnumber the real ones. The original organic beings in the one true base reality would be one, and the simulated beings would be billions upon billions. So, if you accept that, just on the basis of pure cold probability, what are the odds that you are one of the originals? The odds are not good. The odds are statistically overwhelmingly that we are one of the copies. That's the philosophical argument. It's a logical trap. And it's unsettling. But then you ask the physics question. If we are in a simulation, could we know? Could we look for the code? Could we find a glitch? If this universe is a program, it must be running on something. A kind of computer. And that something, that computer, it can't be infinite. It must have limitations. It must have a finite processing speed. It must have a finite resolution. So physicists have seriously proposed looking for this. For instance, is space-time smooth or is it pixelated? Is there a smallest possible size, a fundamental pixel of reality? We have a candidate for this actually. It's called the Planck length, an impossibly small scale, but not zero. Does this mean our universe is digital, that it's made of bits? Some have proposed that if space is a grid, a kind of lattice, then maybe, just maybe, things would behave differently depending on the direction they travel relative to that grid. And they've looked at, for instance, extremely high-energy cosmic rays particles that have travelled across the universe. Do they slow down or stutter in a way that suggests they're hitting the grain of space-time? So far, nothing, no evidence. The simulation, if it is one, is very, very good. But then there's quantum mechanics. This is where it gets really weird and in a strange way suggestive. Quantum mechanics, the physics that governs the very small, it's just bizarre. It's based on probabilities, not certainties. A particle like an electron, it doesn't have a definite position until you look at it. Until you measure it, it's just a wave of probability, a smear of possibilities. It's both here and there, it's spinning both left and right. And then you observe it. And in that instant, all those possibilities collapse into one single reality. This has baffled physicists and philosophers for 100 years. What is this? Why? Why does the universe care if we're looking... Well, if you're a programmer designing a vast complex simulation, you know exactly what this is. It's optimization. It's resource management. Think of a video game, a vast open world game. When you're standing on top of a mountain, the game, it doesn't render every single blade of grass in every single valley across the entire map. It doesn't calculate the path of every single fish in every single river. Why would it? It would be a catastrophic waste of processing power. No, it only renders the things that the player, the observer, is looking at. The rest of it just exists as a set of probabilities, as potential. What if the universe is doing the same thing? What if the simulation doesn't bother calculating the definite state of every single particle in the cosmos until an observer, a conscious mind, interacts with it? What if this strange ghostly wave function collapse isn't a deep metaphysical mystery about the nature of reality, but just the system rendering the asset at the last possible moment? Oh, it's a chilling thought, but it's also a weirdly neat one. It leaves you with, well, a kind of existential dread, doesn't it? If this is all a program, a dream, a dream. Am I real? Are my thoughts my thoughts? Is my suffering, is it real? Is my love for my family, for my friends, is that real? And I think the answer has to be yes. It has to be. A simulated fire still burns a simulated hand. The experience is real. The suffering is real. The joy is real. If the simulation is high fidelity enough to generate a being that is self-aware, a being that can ask the question, am I real? Then that consciousness is real. It exists within the system. Our love, our pain, our meaning, it's all an emergent property of this system. But it's real to us. It's the only reality we have ever known. This world, it is consistent, it follows rules, and that's all that's required for meaning. And what about science? What about our entire noble quest to understand the universe, is it all a waste of time? No, I don't think so. It reframes it. Science is no longer the act of discovering the fundamental timeless Platonic laws of nature. Science becomes the act of reverse engineering the code. We are figuring out the rules of the program we are running inside of, and it starts to make a strange kind of sense. Maybe the speed of light isn't some fundamental property of reality. Maybe it's just the processing speed of the simulation, the maximum rate that information can be passed from one pixel to the next. Maybe the Planck length is the resolution of the simulation, and maybe the fact that we cannot for the life of us unify general relativity, the physics of the very large, with quantum mechanics, the physics of the very small. Maybe that's not our failure. Maybe it's just seam in the code. Maybe there are two different physics engines, two different subroutines written by two different programmers, and they're not stitched together perfectly. And we, in our probing, are just seeing the stitches.
Yes.
Who or what is running it? An ancestor simulation. Are we the historical reconstruction of a post-human civilization trying to understand its own origins? Are we an experimenter, a piece of art? Are we just a child's science fair project in a higher dimensional classroom? We don't know. We can't know. Maybe our simulators are just biological beings like us. Or maybe they are vast, unimaginable, timeless AIs. Maybe they are also in a simulation. Maybe it's simulations all the way down. It's the ultimate question, the one that dissolves all other questions. And we're left just floating in this beautiful, intricate, and perhaps artificial dream. And all we can do is what we have been doing, to wonder, to test the rules, to be kind to each other. Because, real or not, this is where we are. This is our home. We have wandered so far tonight, haven't we? We started with a simple question. That very human, very small four-word question. What came before? And that question became a doorway. We stepped through it and we found ourselves standing at the very edge of time, looking into the singularity, that place where our laws and our language seemed to break down. And when that answer wasn't enough, we looked out for another. We imagined a universe that breathes, an eternal cyclic cosmos collapsing and bouncing over and over in a rhythm that has no beginning and no end. We imagined a vast, restless sea of quantum foam, an inflating ocean endlessly bubbling with new universes, our own cosmos just one tiny accidental bubble in an infinite sea. We pictured our reality as a thin membrane, a brain floating in a higher dimension. Our Big Bang nothing but the fiery echo of a collision with another world in a space we cannot see. From there, we turned our gaze inward. We questioned time itself. We wondered if the past, present and future are all just there, part of a static, timeless block, and our sense of flow just a trick of perception. We touched Hawking's strange, beautiful idea of a universe with no edge, no beginning, like the smooth curved surface of a sphere. And then we took that final dizzying leap. We asked, if this entire intricate, beautiful and terrible reality is a dream, a simulation, a line of code running in a machine somewhere built by someone. We have held infinities and nothingness in our minds all in the span of this short time together. And now, here we are. At the end of this journey, what do we have? Do we have the answer? No, we don't. And I think that is the most important part of this whole story. We don't know. And maybe we never will. Not completely. These ideas, these models, they are the best, most brilliant, most honest attempts by our species to ask the question. But they are still just ideas, stories woven from mathematics and observation. And in the end, we are left in the quiet, in the mystery. We are left with the not knowing. And isn't that beautiful? The purpose of this, the purpose of lying awake in the dark and thinking about the cosmos, it isn't to find the final simple answer. It isn't to solve reality as if it were a puzzle. The purpose is to wonder. The purpose This is to expand. To feel our minds stretch just a little bit. To feel the rigid everyday walls of our perception get a little thinner, a little more transparent. It is to touch, just for a moment, the sheer staggering scale of what is, the strangeness of the fact that anything exists at all. It's to feel awe. That is the value of this, not certainty. But awe, because whatever the answer is, whether we are one iteration in an eternal cycle, or one bubble in an infinite sea, or one dream in the mind of a machine, whatever the truth, here we are, right now. We are the part of the cosmos that has woken up. We are, in a very real sense, the universe's self-awareness. We are the instruments through which this vast silent mystery gets to contemplate itself. The atoms in your body, in your brain, forged in the hearts of stars that died billions of years ago, have assembled themselves into a pattern that is complex enough to lie here in the quiet and ask, what am I? Where did I come from? And in this moment, in this stillness, that is enough. The mystery, it doesn't need to be solved. It just needs to be felt. It's not a problem. It's a privilege. And so let the question just float away. Let the infinities and the singularities and the brains and the bubbles just dissolve. They don't matter. Not right now. All that matters is this moment, this breath, this quiet, this feeling of existing. You are here. You are a part of this vast, magnificent, unknown everything. And you are safe. You are home. And it is time to rest.